All right. Hopefully he will join us soon. All right.
I ain't do nothing. I don't know shut up. He still ain't here.
Okay. Chapter 7 is literally 3 sections long. Okay. It should not take us long at all to get through each section daily. All right. So, what is a network? A network is any connected graph. Okay. So, your keyword here is connected. Okay. A network is any connected graph. So, everything has to be one piece. That's the first thing you need to remember. Everything has to be one piece. We still have vertices, but your dots are now called nodes or terminals.
I thought nodes was that thing the girl had on Pittsburgh.
Lymph nodes, everybody has those.
I don't know what that means.
Okay. So we're kind of getting ready to talk about, telephone poles and the wires that, connect and give you cable. They give you a dial tone at your house. Okay.
You still use a landline.
I don't know who does because I don't. You either got my husband's cell phone or my cell phone. You ain't getting a hold of me any other way.
If you get a call on the landline, they got to the police.
5-0. Okay. Your edges. Your edges are now going to be called links.
Switching it up.
Still the same things. They're still dots. They're just now called terminals because we're talking about a network. You still have the lines that connect your dots. We're just now calling them links. Chapter theme. Our job in this chapter is to find optimal networks that connect a set of points.
Doesn't optimal mean the best of the best?
Best of the best, which means we're looking for small. Okay. We're looking for small in this chapter because, think about it, Verizon has Fios now. It's very expensive.
What's Fios?
Fios?
What is that?
It's like an upgraded network. So now when they have to run the lines between pools, it's very expensive.
Why would they do that?
Because it's faster.
Who's it expensive for?
The people that...
Pay taxes.
So Verizon now has 5G.
I don't have that. I still have 3G.
5G has now come out. But if you want the faster... So our job in this one is to connect all the terminals. So we need to have edges that reach out to all of the dots. Okay? And we want to make the total cost as small as possible. That is our goal. So, ways we can do this. Maybe if my remote will work. There we go. Okay? Ways we can do this. And this is an example of a network problem. The weighted graph represents a system of roads that connect buildings of a company's headquarters. The company is planning to upgrade its fiber optic cables through underground lines connecting its servers. The weight represents the cost in millions of dollars. Okay? So, if they want to run a fiber optic cable between A and E, that's going to cost $3.1 million.
That we do not have.
Exactly. Okay? But again, as we upgrade, as technology gets better, we got to show up more money. Okay? Unfortunately, though, like your jobs don't get raises as we upgrade. It's not, oh, here's 5G. Here, have a $10 raise. We can only wish. Okay? So things get expensive. So they actually have specialists that come in and say, this is the cheapest way for us to run these lines. So we don't have to up everybody's bill by $50. Okay? They try to come up with the smallest route. So we can do that in different ways. The first one, we can create a subgraph. A subgraph are edges that come from the original graph. Okay? So that's one of the things. you cannot create new edges in this chapter. Your edges have to come from the original graph. So if there's not a line that connects the two, you can't make one.
Don't they do the same thing here? The same grades here?
Yes.
A span.
Keep on graph, bro.
A span is a graph that must include all. That's your big thing. All vertices of the original graph. So if they're asking for a span, you have to reach out to every point that's there. You have to have an edge that connects every point. Finally, minimal. This is the total weight of the network. Must be as small as possible. Must be as small as possible. So let's see if we can draw some pretty pictures. I know you're so sick of drawing, but life happens. Okay, so example number 1 says, I want to create a subgraph that has 4 vertices and 6 edges. Okay, the thing is, we have to create it from this original picture. Okay, you cannot create any new lines. You cannot create any new dots. So what 4 dots from the original graph would you like to use that have 6 edges that connect them? Okay, so I can use B, C, E, and F. Because then I can use the 6 edges that come from the original graph to draw this subgraph. There's a line that connects B to E. I have a line that connects B to C. A line that connects C to F. A line that connects E to F. I've got one that connects E to C and one that connects B to F. So again, everything came from the original picture. 4 dots, 6 edges. Nothing new.
What's bent?
It's so nice that you call. Shut up.
Yeah.
What you mean?
Call of the Wild.
Is your what called?
The Mexican call that they doing getting to the song, you never heard of? You never watched Coco?
Oh yeah, you wild. You haven't lived life.
All right, back to spans. Okay, example 2 says I have to have a span. All the span says is I have to have all of the original dots. So I can't lose any of these.
Lies.
Okay, if it's a span, I have to have all. So this is A, B, C, D, E, and F. I have to keep them all. I need to now draw 5 lines from my original edges that connect to all 6 of these dots. 5 lines. What do you want to use?
A to B.
A to B.
D to E.
You said D to E.
There's all the ones on the outside.
Okay. So Gianni says I want to do all the ones on the outside. So you can go A to B, B to C, C to F, F to E, E to D. That is a span of 5 edges. Again, span uses all 6 dots, and we only need 5 of the edges. Now, I could have switched it up. Instead of using C to F, I could have connected B to F. And that's still a span with 5 edges. Okay. It doesn't matter what 5 edges you use as long as you reach out to each vertex. Okay. So this one right below your original says I want to draw a subgraph that has 5 vertices and 4 edges. So you need to pick which 5 vertex or vertices do you want to use. You only need 5 of them, so you just need to get rid of 1. Which one do we want to not use?
F.
You said F?
M. B. D. What do you want?
Any of them.
You good, G?
Why are
Pick
you
one.
looking at me like that?
Because I'm making sure you said F because you had to.
Yeah, F.
Okay.
It's like you said, N.
I thought she said N. I'm like, where's there an N, Zoe? Where are you getting N from? Okay, so she wants to use A, B, C, D, and E. Okay. So we now need to connect those 5 points with 4 lines. The lines have to come from the original graph. So what lines would you like to use?
A, B, C, cross over to E, then go over to D.
That works. Again, each one of these lines, I trace from the original picture. Nothing's new.
You guys know it's supposed to rain this week?
Huh?
You know it's supposed to rain this week?
I have no idea. I do know, however, that instead of using C to E, you could have used this and done B to E instead of C to E. That would have been okay.
I do know.
Okay? I do know that. Okay? So, there's more than one way to do this. Okay? The next example over says, I want a span. As soon as you see the word span, that means all vertices. So I need A, I need B, I need C, D, E, and F. Okay. A, B, C, D, E, F. I need to use 6 edges now to connect these. What 6 edges would you like to use?
A, B, C, F, D,
A, B, C, F,
E, D,
E, D. There's 5.
E, B.
You said E to B. There you go. Okay.
So wrong.
You could have swapped out one of those and went A, B, C, D, E, F, and then done here and here. Okay, that would have been okay. As long as every dot is reached out to by an edge and your edges all come from the original picture. Again, you cannot create any new ones. So I can't make a line that goes from A to D. It doesn't exist. You can't make a line that goes from A to E. It doesn't exist. Finally, the last one. I want a subgraph that has 6 vertices. Well, I only have 6 in the picture, so I need them all. A, B, C, D, E, and F. I want to connect these using 5 edges. What edges would you like to use?
Oh, shit.
Oh, shoot. What did you just notice? You messed up. It's okay. That's why we use pencil. It erases.
Oh, I got it. Oh, wait, I just got the same thing as the first one.
Oh, look. If you actually look at this example up here, it's the same thing.
Yeah.
Okay? 6 vertices, 5 edges. So the subgraph with 6 vertices and 5 edges is the same thing as a span of 5 edges. So I can just redraw what I had right above it. And it works. Bada bing, bada boom. Questions? Okay? Flip the page. Okay, so we started talking about networks. Now I'm going to tell you about a particular network. And this network is called a tree. A tree is a network, which means it needs to be a connected graph. Okay, but a tree has to have no circuits. Okay, when we drew our subgraphs and our spans in the last one, if you take a look, I'll flip back here in a second. If you take a look at this one, we created a circuit. So this one is not a tree. This one here, we created a circuit. So this one is not a tree. But example 2, the one below it, and example 3 over here are trees. Okay? They're all connected and there are no circuits. So that's what we're looking at now. So a network, which means it has to be connected with no circuits. Take a look at A. Would you call this a tree?
C. No.
I heard yes and I heard no.
No.
Gianni, why do you say nah?
It's not connected.
It's not connected. This is in 2 separate pieces. Okay, so this is no tree.
No tree.
It's disconnected. Okay, it's disconnected. You've got 2 separate pieces.
It's disconnected like your cable.
Yes. If I went out and snipped your cable line, you are now disconnected. You have no network.
You could try to snip my cable line, but we got Netflix.
I don't have cable.
We use
It's usual.
I got Netflix.
Wi-Fi.
Yeah, pretty
We don't
much.
even use our Wi-Fi.
Oh, he steals Wi-Fi.
Technically, it's not stolen because they never gave us the code.
Oh, there you go. Well, then no, it's not. Take a look at B.
Damn, why would I do that? That's generous.
We give them $10 at the end of every month.
Okay, take a look at B.
Yes.
Gianni says yes.
Yes.
Does anybody else agree with Gianni? Is this a tree?
No.
Okay, so you got to answer 2 questions. Is it connected?
Yes.
Yes. Okay, so that's first criteria. We're good. Does it have a circuit?
Oh,
No.
see what?
No.
It doesn't.
So it's connected
Everything's connected.
and no circuit. So yes, this is a tree.
Oh, so if it's got some
If there's something closed off, then it's no longer a tree.
okay.
If it has any type of closed off shape, it is no longer a tree. Okay. Take a look at C.
No.
Why?
It's a circuit.
There's a circuit here. Okay, this is no. This is no tree. You've got a circuit right here. Okay, even though it looks like a tree, like an actual tree, it's not a tree. Okay, we're not talking about branches and everything else.
Equilateral triangle on a stick.
Equilateral triangle on a stick.
Or
Is it kind of like Jose Jalapeno on a stick? He's dead. Okay, so there's a circuit in this one. There's a circuit. Take a look at D.
circuit.
That's a tree.
This one is a tree.
I don't know why it's a tree. Always open.
Okay, this one's a tree. Again, it's connected. There is a branch that reaches out to every terminal, and there is no closed off sections. There is no circuit. Okay, questions on the first 4?
A fixed it. A fixed his little frame.
A did fix its little friend. You are so true.
Yeah.
Okay, if you look at E, E is A, but they became friends. They joined together. Okay, so Drew, is E a tree then?
Yeah,
Yes. E is a tree.
that's a tree you can climb.
You can climb that one. Only if there's a ladder though, because I can't. I'm not a tree hugger. I can't. No, I'll hurt myself. I can't. Don't feel bad. Take a look at F.
I wish I could climb a tree.
Is F a tree?
Do it.
No.
No.
Because it's technically circular. I mean,
No tree.
It's a Christmas tree.
Right. It looks like a Christmas tree, but look, I've got a circuit here.
It looks like a tree. It's not a tree.
I have a circuit here.
It's a Christmas tree.
I have a circuit here. I have a gigantic circuit. If you trace the whole thing.
It just must be.
Okay, so there are circuits. So this is not a tree. Take a look at G.
That's a circuit there. No, wait a minute, I lied. That's a tree. Is it a tree? Yeah, it's a tree.
This one's a tree.
It's a tree.
Look.
Ain't nothing closing off.
If it doesn't close off. So I can go here, 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 but there is no closing off.
I
So
was
there
looking
is
at
no
it-
circuit.
I was looking at it from the end.
So there is no tree.
Look, ain't no
It looked like it's like.
I don't know what
Okay.
to call it.
So
Ain't
people
no
last
vertices.
period. So let me stop you here so everybody's on the same page. People last period said, but there's this diamond thing here.
Yeah, but ain't no vertices.
But there's no vertex in those corners of that diamond. So that is not a circuit. A circuit has to go vertex to vertex to vertex to vertex. Okay. So if I would have added terminals here and here,
Yeah, that's-
then yes, you would have had a circuit. Okay. What was that?
That's good enough for a yellow jacket. First down.
Okay, so that one is a tree. Take a look at H.
Yeah, that's a tweet. A tweet.
First down.
So what if I tell you it's not?
Man, no, ain't no circuit. Wait, hold on.
It isn't because it doesn't.
Look,
There's no circuit.
look.
They're not.
Here, 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 here.
Oh.
Uh-oh.
We got a plot twist.
Uh-oh, Skedios. This is not a tree. Because there is a circuit. I can leave any one of these points that I just traced, so I can start here. And I can follow this around, and I can make it back without lifting my pencil. Which means that I have a circuit.
Oh my gosh.
That's crazy.
Okay?
You must have watched a lot of Scooby Doo.
Why?
I'm like, man.
Look at me. Look at me. You just act like the natural.
Yeah, because her brain is fertile.
The prefrontal cortex is no longer there.
Nobody knows what that is.
You know what your prefrontal cortex is? What makes you
Nobody knows what
It's
that
the part of your brain that's literally right here. The prefrontal cortex.
is. Okay.
Go outside.
Yeah, it's on the wall.
No, I like it.
Okay. Questions. Okay. So the next question right below that says, do you notice, is there a relationship between the edges and the vertices of the ones that we said are trees? So take a look at each one we said is a tree. We said B is a tree. How many vertices do I have in B?
It's one list.
Ooh. So if you take a look, I have 11 dots
So you go have 10 lines.
and I have 10 lines. If you move over to D, I have 6 dots and only 5 lines. Okay. If you look at E, I've got 4, 5, 6, 7, and 6 lines. And in G, I have 8 and 7.
G.
Okay. So every time that you have a tree, that's another wonderful criteria. Your vertices are your edges plus 1. Your vertices are always 1 more than your edge. Or we can write it as your edges are 1 less than your vertices. Okay, that has to happen when you have a tree. So if I told you you have 12 vertices and 12 edges, you should be able to tell me right then and there, no tree. Because you should only have 11 edges. Is there a special term that we learned back in chapter 5 that would tell you what each one of these edges are? Go back and look at it. Look at each one of your trees. What would we call each one of these edges?
That's a path.
It is a path.
That's
I'm thinking of something else, though.
a Uber path.
They're all odd, so no, it's not an Euler path.
I said Uber.
Okay.
Can you give us an hint?
What happens?
Does it have a name?
What happens if I remove this edge?
Oh,
What
it's
happens?
it's
Let me see.
Isolation.
It separates it, which means my edge is a?
Isolated. Dang, it start with a D, don't it?
No, it starts with a B.
Bridge.
Bridge! Woo! I so trumped you on that one.
You didn't have to say it so calm, though.
Alright, I just said-
You could have came with a little bit of hype. Bridge! Nah, she said bridge. Like, bitch, I already knew that. Like,
So each one of the edges in a tree is a bridge, which means if I erase it, it disconnects my graph.
I didn't even know that. Stuff you learn, bro. I learned. I'm smart. My God.
Genius. Okay. All right. We have a special kind of tree. They're called spanning trees. Okay. A spanning tree, your formal definition, is a subgraph of a network that connects all the vertices and has no circuits. So, just like we did the subgraphs back on the first page, we're going to do the same thing. But this time we cannot create any type of circuit in it because it's now a tree. Okay. So, if you use what you just figured out, that the edges are always one less than the amount of vertices, that will help you create a spanning tree. Okay. So, for instance, if you take a look at this picture that we're trying to create this spanning tree for, how many vertices do I have?
Seven.
4.
Vertices.
5. I'm sorry.
5.
Oh.
A, B, C, D, and E. I've got 5.
Yeah.
If I have 5, that means how many edges would create a tree? 4. Your edges should be 4. So I need to create some kind of subgraph that has all of the vertices. So I've got to have A, I've got to have B, I've got to have C, I've got to have D, and I have to have E. I need to use 4 lines from that original picture that connect all of these points. Only 4 of them. I cannot go above 4, so I can make it a tree. What do you got for me, Gianni?
Go to E to D. D to C.
E to D.
Just go around the edge. Go straight up.
There's no graph. There's no line there that connects B to D.
Oh, we'll go to,
It has
go to A. Go to D to A.
You said D to A.
Then go from C to B.
C to B.
Oh, well, you got to connect A to C, I mean, though.
Okay. 1, 2, 3. Here's my 4th one. Okay. Take a look. He used lines or edges from the original graph to connect these. And he only used 4, which makes it a tree.
Trey.
Okay.
You know, I ain't gonna lie. I'm trying to do this page. I was like, what is a tree?
Oh my. D and E.
Yeah.
Okay.
Seniors.
Yeah, give me a different one.
No.
4 lines that connect all 4 of these points that come from the original picture. I just don't want to match Gianni's.
That is answering like that.
Give me something. You said A to B, okay?
I could have sworn my phone.
3 more.
No.
C to E, okay? A to D. And you said which one? Is there a line that connects B to D from my original? E to D? I'm sorry, did you say E to D originally and I misheard you as B to D? Okay. So this one works too. Both of those answers are absolutely correct. Okay. Take a look at this.
Okay.
These are all of the examples. Okay. So here's some more of them. Any one of these would have also worked. Again, all of the dots, no circuits, and your edges are one less than than your vertices.
I'm happy sleepy today.
Hard working man.
He is a hard-working man. Okay, questions on a spanning tree? Okay, the last thing we need to talk about.
It's kind of easy.
Okay.
So you don't say that till she smack you with the project. So,
Oh, the project's super fun for this one.
Oh, yeah.
Do you think it's
What
fun?
you
You have to create a network
Oh yeah, you think that?
using a map of the United States.
Bro,
The cities
you
that I
need
give you.
maps. This is
Do we
not-
need a calculator today?
No. Okay.
okay. Jessup used to have coloring in college.
Man, I hate when Jessup be like, color, you gotta color it. Jessup.
Okay. So these are all of the properties that make a tree. Remember, we already talked. Must be connected. Okay. Must be connected. Your vertices have to be one more than your edge.
One more?
All of your lines have to be a bridge. Okay? Which means that there's only one path that joins two vertices. There's only one line that connects 2 points. Okay? So, you should be able to take a look at each one of these and tell me that's always a tree, never a tree, or that can sometimes be a tree. Okay? So, take a look at one. It
That's a
says
tree.
G has 4 vertices, 3 edges.
No.
G stands for graph, not Gianni.
Hey.
Okay? He got a big old ego there. He's just like, hey, she don't know.
No, he
me.
was just happy that somebody was finally talking about him.
You're not that boy, bro.
Okay. So,
Hey, yeah.
Zoe says that number 1 is always.
It is a tree.
Okay?
Can we just
So,
write
I
one?
can draw this as a tree. Here's 4 vertices. Here's 3 edges.
Yeah.
That's a tree.
Yeah, why not?
But, take a look at this. This is a tree.
That was funny.
I can also do this, though. It says 4 vertices and 3 edges. That's 4 vertices and 3 edges.
But it ain't connected.
Is that a tree?
Nah.
No.
So it's sometimes.
This is not. So this is sometimes.
Yeah, why not?
Okay? Number 1 says nothing about it has to be connected. It says nothing about there are no circuits. It says nothing about being bridges. So I can have a disconnected graph. So that's what makes this sometimes. Yes, it can be a tree, but it also cannot. Okay? On your test when you get these, if you pick sometimes, you need to draw me a picture that is sometimes a tree. So yes, I have a tree, and no, I do not. So you'll have to give me the 2 individual pictures. Okay? Take a look at number 2.
Man, that's a all the way.
It says G is connected with 4 vertices and 3 edges.
Oh, I was going to say, where did you... I don't see connection in that sense.
G is connected. From number 1 to number 2.
That says connected in number 2.
This says connected. That word connected changes number 1 to always. It's the same exact thing, except I shoved that word connected in.
She shoved it in there.
I shoved it in.
Yeah.
I just took it and went, "Whoo!"
Shoved it right.
Oh.
Shoved it right in there. You're right.
I knew that
She
you
got
got
the 2 details.
a little dance.
All right. Take a look at number 3. We have 5 vertices and 5 edges.
I got it.
Give somebody else a shot.
No, I want
5 vertices and 5 edges. What do you think, Jesus? 5 vertices, 5 edges. So 5 lines, 5 dots. Would this be a tree, sometimes a tree, or never a tree?
I'm trying to put this tree on. It ain't gonna
Think about what we just came up with over here.
Bro, it ain't
Why?
gonna be no
Because it has to, like,
Wait.
I agree that
I
this
just know
is
it
never.
doesn't.
Jesus says he knows it isn't, but he's not sure why.
I got you, bro.
What?
Because it.
Not necessarily. Oh, Gianni says I have too many edges. Remember, a tree says if my vertices are 5, I should only have 4 edges. There's too many edges, so this is never.
Ooh, lady. Oh my.
I don't think there's no such thing as too many edges. You feel me?
I mean,
In this
Well,
sense,
Yeah,
There's too
there
many
can
edges.
be. It can be. It can be.
or maybe we should make it not enough vertices.
Yeah.
We could also write not enough vertices. Take a look at number 4. I have 5 vertices and 4 ridges.
Oh shoot, I didn't even notice that when I did.
Ridges.
That's-
Always, sometimes, or never.
oh, wait.
What do you think, Timothy?
Always.
Always, sometimes, or never. 5 vertices, 4 bridges.
Sit down,
What?
take me part.
Say it louder. Be proud.
Always.
Always. Timothy says always. Okay? This is always because they're telling you that your edges are bridges.
So that means none of them are
Okay? So that means there's no circuits. These are bridges.
Yeehaw.
So watch your words. Yeehaw. Did we move to Texas? Okay? Number 5. 10 vertices, 9 edges. What you got, Gianni?
Sometimes.
Sometimes. Okay?
Sometimes.
This is just like number 1. Okay? You have the right amount of vertices and the right amount of edges. But this does not say it's connected. Okay? It doesn't say I have bridges. So this is just like number 1. Take a look at number 6. Drew. 10 vertices, 11 edges. 10 vertices and 11 edges.
How this gonna work, right?
Always, sometimes, or never.
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 One more edge over the rest.
Right. This is never. If this was a bridge, or I'm sorry, a tree, this would have to be 9, or this would have had to be 12. And he just gave out. Did you see
Ooh, I
that?
seen that.
Oh,
I was about to-
that just means old.
I was about to get up and kiss.
Ooh, I thought you were gonna have to.
Y'all ugly.
And he totally just gave out on me.
You know what that mean, right?
I'm old.
You can say I'll vote.
Stop. Stop.
Sorry.
Zoe.
I can't help it today.
Oh my God. All right. Anyway, moving on. 12 vertices and 11 bridges. 12 vertices and 11 bridges. James. James, what do you think? If I have 12 vertices and 11 bridges, would you consider this always, sometimes, or never? Ask yourself this. Are your edges one less than your vertices? Do I have one less edge than I have vertices? James, don't be shy. Come on. I got you. Look up here. You're okay. I have 12 dots. This means I have 11 edges. Is that one less than 12? 11?
Oh, yeah,
Yes. Okay. One less than 12. My keyword here, James, is bridges. Because it's a bridge, that means it's not
Your spot really
closed as a circuit. So this would be
Yes.
always. This one is always. Are you dying back there? Okay. The last one. Think about what this is saying to you. Okay. This says I have 8 vertices and every vertex is a degree of 7.
It's off the way off.
That's all the way off. This is definitely a never. Okay? If I have this graph and each one has a degree of 7,
What's going on?
that means I've got a dot and each dot has 7 lines coming out of it. That's way too many edges.
That's what my life
Because then
is.
I've got another one over here that has lines coming off of it. Never gonna work. You tell me what's 8 times 7.
56. I was-
Thank you. Whew. It's making me nervous.
56 grams in the blunt last night.
All right.
Okay.
Okay. You have homework.
Of course we do.
Of course you do. Okay. In Canvas, you will find chapter 7 book pages. You are doing numbers 1, 2, 3, 5, and 7.
I can remember that.
because I'm a genius.
1, 2, 3, 5, 7.
Or it really could be the fact that I wrote it over there on the board, right here, in orange,
Oh, I see. Yes,
so I can reference it.
I got you.
So what's